I looked at angular momentum as an idea, and this is going to be a video that does angular momentum as an example. A figure skater is probably the most common way that you're going to come across this, so I will do that first. Let's say you have a figure skater who is spinning in circles. So something like this. Here is the ice, and they are spinning in circles about a central axis that would look like this. Maybe they are making 1 revolution per second, which of course we're going to end up having to convert, but so be it. 1 revolution per second. With arms out, with all of everything, maybe we get a moment of inertia of 2.5 kilogram meters squared. It doesn't seem like a lot, but it's actually quite a bit, because you are looking at definitely distances that are smaller than a meter. You're squaring those, so things slow down, or things that moment of inertia gets small fast. In section 5.2.2, we did look at moment of inertia, and one of your examples was figuring out a moment of inertia for a person like this. So we're going to do this, and then the figure skater wants to speed up. So instead of being all reaching out, we're going to tuck as tightly as possible while still standing, while still spinning. And we'd like to figure out the final rotational speed. In this tucked position, we can get down to maybe 0.4 kilogram meters squared. Our initial angular momentum is L initial is I initial omega initial. Our final angular momentum is going to be I final times omega final, that's L final. And what we would like to do is set these equal to each other. When we do, we get omega final over here equals I initial omega initial over I final, and we can plug in 2.5 kilograms kilogram meter squared times omega initial. Now here's a problem. I have omega initial in terms of revolutions per second. Ultimately, my I and I, the units on those are going to cancel out. So if I just leave this in revolutions per second, I'm going to end up with an answer that's in revolutions per second. And I can do that. I'm going to do that for right now. I'm dividing by my final, which is 0.4 kilogram meters squared. And when I do that, I get a final speed of 6.25 revolutions per second, which is fast. You're spinning around 6 times in 1 second, but if you've watched like Olympic figure skating, they do spin really fast. So 6.25 revolutions per second. Now we might ask something like, was there energy loss? How did the energy change? Because that's worth asking. To find what the energy is, we're going to have to actually get these numbers as radians per second. So 1 revolution per second 2 pi radians is 1 revolution. So we get 2 pi radians per second, or 6.28 radians per second. In the end, we get 6.25 revs per second times 2 pi radians per 1 revolution is 12.5 pi radians per second, or something like 39.25 radians per second. So how did the energy change? Well, let's find out. Our initial rotational kinetic energy is going to be half I initial omega initial squared. I can plug in half of 2.5 kilogram meter squared times my 6.28 radians per second squared, and I get 49.3 joules. Then my final, I'm going to go again, half I omega squared and now it seems like, what is going on? I have somehow or other gained 250 joules of energy. Does that make sense? Where did that energy come from? It does make sense. If I am spinning pretty fast, my arms want to kick out, my legs want to kick out, my limbs are being pushed to the outside. If I'm on a tire swing, maybe, my body wants to be thrown back. So if my body wants to be thrown back, that means it's taking force. It's taking me putting in effort to hold my body inward. It's harder to be in this tucked fast position than it is to be in this loose and wide position, which means to go from the looser, wider position to the tucked position requires effort on my part, requires energy, force output. In doing this, in going from here to here, I have to do work. I'm no figure skater, but in this case, let's say I am. I have to do whatever this difference is, 308.1 joules minus 49.3 joules equals 258.8 joules. I have to do 258.8 joules of work to make this happen. I don't get to speed up for free. It's still taking effort. So that is angular momentum conservation and looking at what's going on with the energy, which is a serious question too.